they have a lot of energy management. Basically, if you look at your perimeter, it looks like this. You have energy everywhere. Okay? So in this case, how can you still say you can make a group of the cluster and say, okay, this belongs to one hard object from Quark group or WJ object. They are not the background. So we have a different strategy for that. One strategy is this. So we know that 20 more minutes? Yes. We know that if you have a pile up, the pile up is a process that you have some other soft interaction happen in the event. So for each soft interaction, they will, in average, deposit the continuous energy popular over a detector. And you can also imagine that when you have the more number of pile-ups show up, the average energy deposited in the detector will be linearly proportional to the number of interactions. So we can apply this idea. What we do is that when you define a group of the jets, and you have a jet area, then what you can do is that you can subtract, if this is the jet area, you can subtract, this is the density. This is the density that what's the average energy deposited in a single cell per area, okay? So then you can have the original reconstructed momentum, and you subtract the jet area, and these are some fine corrections from the number of prime vertex in the dependence. So what we see magically with this simple pile-up subtraction method, this plot shows the pile-up jet multiplicity. That is, you produce the inclusive dijet samples, and you just count how many number of jets greater than some transverse momentum count. Then you can see that you can count a huge number of jets as your number of detection increase. But we knew that this, in principle, just have two hard jets in this event. So this additional jets, they just come from the pile-up. But then after this area subtraction, and you recalibrate the momentum of the jet, then if you do the counting again, you can see that you basically remove those non-necessary pile-up jets, okay? Then also this the multiplicity actually quite the increase as function of number of vertex significantly reduced. So this can echo to the question that Xiangnan asked earlier in the morning, how we control the pile-up when we go to in the future high energy and high velocity scheme. But yeah, so this is simulation. So so that means that we have to verify this with real data when we have that. Okay. And here, let's see a different way how the subtraction performance looks like. So you have a distribution of the jet mass. So this is a Monte Carlo that we produce some extended gauge balls of like Z prime, TK2 TB bar. So when and then you look at the scenario that you have the jet reconstructed. Okay, so you can see that without the pile-up, you can see that the open circle here. And if you start adding different number of interactions into the simulation, the jet mass start increase. And this increase just comes from you have another pile-up, they deposit energy to your jet area of your hard jet. So after this the jet area subtraction, you can see that you significantly remove those pile-up dependence, and you basically get a nice jet mass distribution, just very similar to the low pile-up case. Then you can really use this correction in order to identify whether you have a really interesting jet you want to study. So other than the jet area subtraction, there are also the huge development about how we have strategy to remove those uncorrelated constitution inside your jet. We call this jet grooming technique. So there are three big families so far that quite popularly used in this study. Let me go through one of them just as an example. A technique called filtering. So this is a jet which is composed of this jet constitution. So what you can do is that you can rerun your jet classing algorithm, but instead of look at the jet classing to the very high radius, and you can just run it with some smaller radius. Okay. So now you can see that I have a 4 jet subjet inside this big jet. So I could apply some criteria. I can drop the subject whose subject mass compared to the total mass. This ratio, if it's less than some number, then I can drop it. Motivation is that if this subclustering, they are actually not coming from your original quark gluon, but they are coming from some unconnected pile up or some soft radiation that dilute the kinematic description of your jet. Then you want to throw it away, and then very likely they have a relatively soft mass drop ratio. So then see that in the end I have a new jet that I remove those unconnected clustering. Okay. So there are also different technique. They have different ratio to doing this kind of cleaning process. We can discuss more detail in our discussion session. So this cartoon shows how this filtering works. For example, you have originally have deposition of the cluster in this pseudo rapidity. Sorry, in this case I throw the rapidity. But if you consider the jet constitution to be a 0 mass, so this is doesn't matter anyway. Pseudo rapidity equal to rapidity. So now I apply some criteria to clean up some soft clustering. Then I run the subject clustering. I have 2, and then I apply some ratio. Then I remove the one that have a lower mass ratio. Then I come up with these 2. Then I run the subject clustering again. Then I try to clarify if they have the same. They satisfy the mass drop ratio, and they sustain. Then I continue to do that, and eventually I can clean up to the point that I clean out those really soft clustering that I consider them not connect to my original quark gluon. Okay, so how this algorithm could perform? Here I start with the original one that I have the open circle with the original jet without pile up. Okay, so if I try to apply the pile up correction, I can improve. My rate will be more closer to the open circle, open instrument. Yeah? Or if I apply some grooming process, okay, then I could also improve the mass shape of my jet, because I remove all those uncorrelated constitution. And if I apply the 2, I also do the grooming, then I also do the jet area subtraction, I get the optimal performance. Yeah. So these are the 2 powerful tools that we try to develop so far. Either using the jet area subtraction or using the jet grooming process, we can significantly improve or reduce the pile up impact to our physics study. So all the work I mentioned here, they are all multiplied theorists. So I have to say that currently the development of the geostructure area, the experiments are one half behind the theory progress. Okay? So I give one example. This is what my current research focus so far. So we have the process that you produce the quark-gluon jet, and then you start doing this showering process. Okay. So what the jet clustering process actually, we try to go backward to recluster those small constitution back to my original jet. So the way we do it right now is actually the way we do the clustering and the way the physics, how they do the showering, they are actually, if you look at the process, they are not the same process. One of the reasons is that the showering process for each branching point here, it's a quantum process. But when I do the clustering, if you recall my procedure, it's a one determinant procedure. Yeah. So what we do right now is that why don't we try to apply this concept? Maybe I can introduce, when I do the clustering, I can introduce some quantum process. Instead of using one procedure, one path to reconstruct my jet, how about I use multiple representation of one jet, then try to squeeze out some representative number.
When you say quantum, here, do you mean stochastic?
I say random number. The way practically we do random number generation to. So the way we do is here. Okay. So when I do the clustering, every time I have a pair of the object, ij, then I introduce a weight. And this weight have a free parameter alpha. We call it the rigidity. And then d here is just the distance of the two objects. Distance is defined in the eta phi prime, the angle. So I have this weighting function. I throw a random number to get the weight and to accept or reject this pair of the clustering. So when I do this, I basically, instead of one single process, if my Ej is equal to the minimum, basically weight is 1, that means I have no random process. So I fall back to my original jet clustering algorithm. But if it's not 1, then I start introducing some random recombination of the recasting of my jet. So one example here, if I use my original method, I have a jet. This is one single jet. I have one estimate of the mass of this jet. This is the black value. Okay. But now I use this random process. So for each jet, this is a single jet. I could have now get a representation. Each one is a new jet mass estimate of this jet. So now I have a distribution to describe this jet, but not just one single process to describe it. And if I look at the background process, compared to background means that it is a quark-gluon, compared to color singular object like WJ, you could see that the color singular object, it has a relative narrower width compared to the QCD jet, which have a more wider distribution. So with this method, I could introduce a new discriminator to discriminate the color singular object and the color object. So we define volatility, the ratio of the width of distribution divided by the average of the mass. So we know that if it's a W jet, then this volatility will be small. But if it's a QCD jet, the distribution will be wider. And then we can use this as a new jet substructure variable try to discriminate the signal background. Okay? So this is an ongoing study process that we hope to get a better understanding of that. So what we do, for example, we have 3 different grooming techniques. We have more than one tagging variable. Then I just introduced you a new method called QJet. And now we try to do a systematic study to identify what's the optimal combination of the grooming and tagging method we can use. And this is an effort actually in parallel, both the bigger theory community and the experiment community trying to do an independent study. So it's usually found situation that experimentalists try to think about the realistic case, how detector will behave. But theorists would like to try very creative idea, trying to use that. So, I think that in this case that one reason why experiments kind of behind the progress is that we try to think from a detector point of view. So there are many restrictions on how a detector really behaves. This is actually an area that's very active. So if you are interested in working on this, for example, Shanna is working on this. So welcome to initiate more discussions. So actually, I think I would like to stop here because it's about the time. Yeah. But as I mentioned to you earlier, like the big summary slide show you that consider all the cinema process. We have a quite nice agreement with the real data. So tomorrow, what I'm going to do, I will highlight some of the creative analysis idea. For example, how do we measure the total Higgs width, and where we think we should try to prioritize first to look for new physics signature. And then I'd really like to also point out some new developments beyond the large hadron collider. Okay. Thank you.
Okay, any questions to Professor Xu?
Yes.
So you discussed many technicalities for dealing with the jets.
Yes.
So practically, what are the major applications of this studies? Because I tend to think the people may already develop lots of tools for the LCC technique data.
Oh no, actually no. In this area, this is new actually. For example, the theory proposal is 2012, and I carried out the first performance study in 2013.
So what are the physics goals?
The physics goal is there are twofold. One, the observable, which could be calculated, so we can compare to the perturbative QCD calculation. So we can understand the jet structure better of different jets. And also the jet here is not just a quark gluon. If we have this color sinking object decay to the multiple quark in the final state, those are the structure that we can compare to the perturbative QCD calculation. So we can further advance the QCD theory. And in testing my purpose, what I really intrigued to do is I will mention more tomorrow. Actually, this scenario, like the reason why you have highly boosted W on top, you could have standard model sources, but there are many Young model theory actually predict this kind of high PT, high boosted object. So we have a new tool that if we can further improve the discrimination from the QCD background, we can make the discovery early. Yeah.
Using the entirely superconducting box?
There will be one idea. Yeah. For example, I could have graviton decay to 2Z boson, or I could have graviton decay to 2 Higgs boson. Then they all go through the hadronic decay. For that, what the need is the trigger, the design a public trigger for that. Yeah. But it's open the new opportunity how to do those kind of study.
Okay, that's it. Shaman?
For the pile up, okay, you mentioned that you do the area correction. Okay, yeah, right. Okay, I wanted the parameter role is the density. Okay,
Yeah, that's
could be
yeah.
energy dependent. Could be energy dependent, right? So
Yes. So when you go, yes, right.
so you go to higher energy,
Yes.
and then this role will change. So
Yes.
if you go to the next page, I see the example you consider. Okay, what's the typical jet energy here? The PT.
The
Yeah, you consider.
PD for this example,
Yeah, for example, PT.
the 500 GeV.
500.
So no, 1 TeV. 1
So
TeV.
you
Yeah.
change it to 2 GB. Okay, have you tested it?
No, okay, there are two things. One, when you say energy dependent here, rho, it's the energy dependent of the proton central mass energy, not the jet energy. Yeah.
It also depends on jet energy. Logarithmically.
But it's part, it comes from higher up. Higher up should be coming from hard physics. The jet energy itself is the
But I want to say, because of the energy density within a single jet
Yeah.
will depend on the PT. So when you see this energy change, you are not sure if the change comes from higher or come from the
oh yes,
higher
you're
energy,
right.
So,
Yes. So this is a statistical average subtraction, and I did not ask a question like event by event difference. So it's difficult, yes, but practically in experiments, we are going to accumulate a lot of collisions. Then we can look at the final statistical distribution. Yeah. So yes, I agree with you that for this, if I want to say a concrete idea for this single event, what's the real jet energy for that? There's a caveat here because we have a chance to over subtract or less subtract the energy.
Okay, any more? So now we are going to have 3 discussions.
Okay.
Okay, let's thank the Professor Xu first. I think we are supposed to meet each other at 5:40. Organizer, is that in front of? So we are. The bus will be ready.
Bus will be ready at 5:40.
In where? Is
Just in front of the square.
okay. Okay, now is a free discussion time.